But then the quantity of liquid or the gas that was in the volume here is the same as that is what is occupying here. But because here it was compressed, it was seen to be small. But because it expanded, now it's no more, there's no pressure affecting it.
Okay.
Yes. So the quantity is the same, but the volume of the container just changes.
Okay.
Yeah. So I don't know, they have the V over the cycle from 1 to 3 and 3 to 1 to be 0 because the volume is still the same. We have, if let's say the quantity of item in that system was, let's say, the mass was, let's say, 5 grams, it's still the same as 5 grams because nothing has changed. Okay. Now the net change in volume, the property during the cycle is always 0. Yes. This means that the cyclic integral of volume, or for the matter, any other property, is 0. Conversely, a quantity whose cyclic integral is 0 depends on the state only and not the process part. So if you are talking about a cyclic process whose integral is always 0, that's if we change the state and I don't believe you are getting 0. It means when you're talking about the thermodynamic part, it all depends on the state. We don't really care about the path. Please, I hope it's understood.
Yes, sir.
Okay. That's taking the equality sign. The equality of that, the quantity of that, the first or that is the Q over the T must represent a property in the differential form. This property is called the entropy, and it is designated as S, that's capital S. But note, we have entropy as capital S and entropy as small s. So the capital S is for extensive property and the small s for intensive property. Note that. Okay. Now, entropy is an extensive property of a system and sometimes referred to as total entropy. But entropy per unit mass, designated S, is an intensive property. So when I'm talking about the small s, it's an intensive and the capital S is for extensive. As I said, note. And has the units kilojoule per kilogram per Kelvin. That's the unit for the entropy, is kilojoule per kilogram per Kelvin. Now, the term entropy is generally used to refer to both total entropy and entropy per unit mass, since the context usually clarifies which one is meant. Now, integrating equation 1.3 between the initial and final states gives, so we are talking about this expression. Okay. Now, we are integrating it from the first entropy state to the second entropy state so that we get this. So change in S is equal to that. And if you integrate this, you are going to get from the first second state to the first state. Okay. Equation, and as we said, the Q over T is a Cauchy's law statement, inequality. So the rate of change of heat energy with respect to what temperature of a system is referred to as entropy. Okay. So equation 1.1 actually defines the change in entropy rather than entropy itself. So this is a change in entropy rather than entropy itself. But you should also know that change in entropy is the same as entropy. I hope I'm not confusing you or the book is not confusing you. They are saying what we are seeing in equation 1.4, we are referring to as for a change of entropy. Why? Because it was from the first state. I'm sorry. We are trying to find the difference between state 1 and state 2. So it means entropy that's with respect to change. So it's called change in entropy, and that is not entropy itself. But it's also known as entropy in the sense that always one state is known to be 0, or the initial state is always assumed to be 0. So that when you are talking about the second state, it will be that of 0 minus that. So whatever you get is the entropy. I don't know if I'm making sense though.
Sir, please come again.
I said, now from this equation 1.4, you realize the entropy they have here is change in entropy. So if you are talking about equation 4, they are saying it's known as change in entropy. They are saying it's known as change in entropy rather than entropy itself. And I'm saying, even though they are saying it's change in entropy, but in ideal sense, it's the same as entropy. Why? Because when you are looking for the entropy change, always the first state is assumed to be an absolute zero temperature state or entropy state. Okay, so the initial state is always assumed to be zero. So that when you go to the second entropy state, whatever you get, if you subtract a zero from it, it's still the same thing, and that is known as the entropy. So in as much as this as change in entropy, it's also the same as entropy. Madam Fisher, is it okay now?
Yes, please, sir.
Okay. Now, we remember energy was also defined as change instead of energy itself in the treatment of the first law. Absolute values of entropy will be determined based on the third law of thermodynamics. Engineers usually are connected with changes in entropy. To this end, the entropy of a substance can be assigned a zero value at the arbitrarily chosen reference state, and the entropy values at the other states can be determined using equation 1.4 by choosing state 1 to be the reference state at s equal to 0 and state 2 to be the state whose entropy is determined. So as I said, always the reference point is always assumed to be at 0, so that the one that you are looking for its entropy is now determined. So it will be that of the one determined minus 0. So whatever you get is the same as entropy, rather than saying entropy change, as I just explained. Okay. One needs to know the relationship between heat and temperature before the integration equation 1.4 can be performed. In the relation, it's not available, then in the relation, if it's not available, then tabulated entropy data has to be used. Note that entropy is a property. Entropy is a property. Okay. Entropy is a property. And like all other properties, it has a fixed value at fixed states. So example is, let's say, specific heat capacity of metal. And not just any metal, let's say copper. So if you take the specific heat capacity of copper, it's the property of copper. It means any copper that we take has that same value. The same thing applies. So if you take the entropy of a certain system, it's fixed. So irrespective of the quantity of that system, whether more or less, the entropy is still the same. Okay. Therefore, the entropy change, that's the S between two specified states, is the same no matter what path. So if we take two two systems and they have the same entropy, or the change between the two entropy is the same, it means whether you go the forward way or the reverse way, or we go the long way before achieving that, or the shortest possible way before achieving that, the entropy is still the same. So assuming if it's 10, so let me use this as an example. Assuming maybe you are coming from Accra to Cape Coast, and they say from Accra to Cape Coast is, let's say, 100 cedis. Okay, and we are using the 100 cedis as the entropy property of from Accra to Cape Coast, that two system. Okay, so for the first state is Accra, the second state is the Cape Coast, and the entropy of this state is, let's say, 100 cedis. It means one can choose the main Accra to Cape Coast road. It's the same as 100 cedis. One can also choose to go and pass Kumasi and those kind of places before it comes to Cape Coast. Irrespective of wherever it passes, it's still the same 100 cedis. So it's a property. That's what we mean by this statement. Okay. So if you look at this state, we have first state and second state. Someone could choose to go this way. Someone can also choose to go this way, whether reversible or irreversible. The state is still the same. The entropy is still the same. So if you look at here, you have the first entropy state to be 0.3, the second entropy state to be 0.7. So if we want to find the entropy of the system, it's a matter of just subtracting 0.3 from 0.7, and you are going to get to 0.4. And as we said, entropy always, we take the absolute one. So likewise, if you are going this way, is it the same thing? It's the same as the 0.7 minus the 0.3, and you are going to get 0.4. So entropy is a property, and it does not depend on the path. Whether reversible or irreversible, it's still the same. Okay. It is also to be noted that the integral of the Q dt, that's the differential of heat with respect to temperature, gives us the value of entropy change only if the integration is carried out along a reversible path between the two states. And they are telling us that when we talk about the entropy change, okay, and we are relating it to entropy, when you take the Q dt, that is changing heat with respect to temperature, to find the entropy change, you always take the reversible path between the two states. Realize here you could take the reversible or the irreversible, and we said all change. But if you are talking about respect to the Q over T, the Q over the T, you realize this one, you are just going by the change in S. So the change in S, whether reversible or irreversible, it makes sense. But if you are going respect to the rate of change of temperature, respect to temperature, we say we always go by the forward, the forward or the reversible part. The irreversible is not possible. Why? Because assuming I have some heat energy and it has some sort of temperature, right? And this temperature is being transferred into a system for it to do work. Can there be a situation where the system is cold? We are talking about not ideal something. We are talking about rare natural situations. To say we have a car, and what the car does is we are supplying heat to the car, and then the car will be doing work. Can there be a situation where this system that needs heat is rather producing heat to the environment? In natural sense, it doesn't work that way because the thing needs work, heat to work. Why is it then now giving out heat for it to work? So it doesn't really work. So it's always the reversible reaction that, the reversible reaction that is always applied when you are talking about in terms of changing heat energy with respect to the temperature. Okay. The integral of the Q dt along an irreversible path is not a property, and in general different values will be obtained with integration carried out along a different reversible path. Therefore, even for a reversible process, the entropy change should not be determined by carrying out this integration along some convenient imaginary reversible path between the specified states. Okay. So now let's look at some example. I think I'll leave it for you, but let's read it. They said that the cyclic integral of work have to be 0. That a system have to produce as much work as is consumed to complete a cycle, and they say explain, and the solution is here for you. So please, we've laid the foundation. You read it to get understanding. If there is any confusion, then you create awareness. Then we go over. So with this, we can go now to the irreversible change. Okay. Now the entropy S is defined, but please, is there any questions so far? Is there any question?
No, let's go on.
The entropy S is defined in terms of reversible changes of heat. Since S is a state function property, the integral of S around a closed loop is 0, so that when you find that of the irreversible of the Q with respect to T for a closed loop is equal to 0. Okay. We will now consider a loop which contains an irreversible section. Section. And a reversible section as shown in figure 3. So if you look at figure 3, where's figure 3? Yes, so figure 3. So we have this reversible and we have this irreversible. The reversible is the downmost one, and the irreversible is the uppermost one. Okay. The gradual inequality implies that integrating around this loop, we have, so if we integrate with the loop, we have that of the Q over T is less than or equal to 0. Now let's try to expand the left-hand side. So when we expand the left-hand side, we have the Q over T. That's from the first to 2 plus that of the. So if you take this loop, right, it's the same as integrating from here to here plus integrating from here to here, even though it's a cycle. So when you do that, you have to get the same as 0. Why is that? Because we said it's a cycle, and for a cycle, the beginning and the end always is constant. So if we add that of the integral from this point plus that of this point to it, we have to get 0. So we are trying to integrate from here to here, then we integrate from here to here as well, and that's what is done over here in the left-hand side. So the entire system is the QT and the Q over T. Now we take that of the irreversible and take that of the reversible, so that when you add them, it must be less than or equal to 0. Okay. Now when we rearrange this, we get back to this. And it makes sense. So you are trying to eliminate the 0 so that this will just come to this point and if not change anything. Okay. This relation holds true, however, closed state and this relation holds true, however, closed state 1 and state 2 get to each other, and so in general we can write the change in entropy ds as. So the whole thing is known as the entropy change, because we move from the left to the right, and now we are putting them in terms of integral form from the first loop to the second loop, so that the entropy change is the same as this. Please, I hope you are making sense. Okay. The equality in the expression is only obtained if the process on the right-hand side is actually reversible, and they say this only holds if the right-hand side is reversible. Remember that because S is a state function, the entropy change in moving from 1 to 2 is independent on the root. So as you said, sometimes the entropy change in moving from the first state to the second state is always independent on the roots. As we use that of the Accra to Cape Coast as an example, it doesn't really depend on the roots, but you know that at the end of the day, 100 cities is what you are going to get. So it's independent of the root. In another way, they say it's conservative property because it's not path dependent. Okay. Let us consider a thermally isolated system. In a thermally isolated system, the Q is 0 for any process. So when you are talking about thermally isolated system, means at the end of the day, there's no heat transfer between the system and its environment. There's no change in temperature or no change in temperature. And if the temperature is 0, it means now that the Q is equal to the whole system is 0, because this over 0 is 0. So that half our ds greater than or equal to 0. Because we take this and that of the last one. And now since the whole thing is 0, it means the entropy changes greater than or equal to 0. Please, I hope you are making sense. Yes.
Yes.
Okay. Now, this equation is very important, and it's in fact another statement of the second law of thermodynamics. It shows that any change for this thermally isolated system always results in the entropy either staying the same in the reversible case or increasing for an irreversible change. This leads to another form of how to state the second law of thermodynamics, that the entropy of an So the second law can also be stated that the entropy of an isolated system tends to a maximum. The entropy of an isolated system tends to a maximum. Now, equation 1.10 can also be expressed as the entropy of an isolated system during the process always increases or in the limiting case of a reversible process remains constant. In other words, it never decreases. This is known as increase in entropy principle. So this statement is known as the increase in entropy principle. Please take notes. Take note of the increase in entropy principle. Okay. The inequality sign in the relations above is a constant reminder that the entropy change of a system during an irreversible process is always greater than the entropy transfer. That is, some entropy is generated or created during an irreversible process, and this generation is due entirely to the presence of irreversibilities. The entropy generated during a process is called entropy generation and is denoted by Sgen. So the Sgen is telling us that the entropy is being generated or the generated entropy. Okay. Keeping in mind that the difference between the entropy change of a closed system and the entropy transfer is equal to entropy generation, then equation 1.9 can be written as this. Please, is it clear? Okay.
Yes,
Okay. Note that the entropy generation, Sgen, is always a positive quantity or zero. So is the S generation or the S generated, the entropy generated is always equal to zero or is a positive number. Okay, so it means at the end of the day, it's being generated. It's not being or generated or created. It's not being absorbed from the system. Okay. Also, in the absence of any entropy transfer, the entropy change in the system is equal to the entropy generation. So in the system where there is no entropy transfer, the entropy change of a system is equal to that of the entropy generation. Okay. Entropy is an extensive property. Because of this, the total entropy of a system is equal to the sum of the entropies of the parts of the system as shown in figure 4. An isolated system may consist of a number of subsystems. So if we take this thing, because we said entropy is an extensive property, if we take this whole thing, we can have sub-generated systems in there. But when you take the whole sample, the entropy within it is constant. I hope you are making sense.
Yes, sir.
Okay. Now, a system and its surrounding constitute an isolated system since both can be enclosed by a sufficient large arbitrary boundary across which there is no heat, work, or mass transfer. Therefore, a system and its surroundings can be viewed as the two subsystems of an isolated system. And the entropy change of this isolated system during a process is the sum of the entropy changes of the system and its surroundings, which is equal to the entropy generation, since an isolated system involves no entropy transfer, so that the total or the entropy generated is the same as the total entropy of the system, and it's given by that of the entropy of the system plus that of the surrounding entropy must be greater than or equal to 0. As we said, when you take a system and the system has no temperature or thermal relation between its surroundings, always the total entropy of the system is the same as what the generated entropy. So the first one holds. And now what if there is some transfer between the system and its surroundings? It means the entropy generated is the same as what? That of the system plus that of the entropy by the surroundings. That would be the total of the entropy within the system or the entropy generated. They say always this is greater than or equal to 0. So in this case, you are not assumed to get an entropy generated to be negative value. Okay. Here, the equality holds for reversible processes and the inequality for irreversible processes. So always when you are talking about the reversible, we can talk of just the straight one. But if you are talking about the irreversible one, that's where we talk about the inequalities. Okay, so with this one, this inequality holds for the irreversible reaction. Whilst this one holds for the reversible reaction. Okay, so anytime you see an entropy sign and it's equated to something, then you should know that that entropy that we are talking about is a reversible one. But if you see it and we are using either less than or equal to or greater than or equal to, then you have to know that we are talking about the entropy as irreversible state or cycle. Okay. Note also that the entropy change of the surrounding refers to the change in the entropy of the surroundings as a result of the occurrence of a process under consideration. So when we talk about the entropy change of the surrounding, it's occurred as a result of the occurrence of the process under consideration. Okay. The increase of entropy principle does not imply that the entropy of a system cannot decrease. The entropy change of a system can be negative during process, but entropy generation cannot. Okay. I hope you are taking note of some of these things, because I initially stated that entropy can never be a negative value, but now they are giving us conditions where entropy can be a negative value. Okay. The increase of entropy principle can summarize as follows. So this is the piecewise expression for the entropy generation. So when the entropy generation is greater than 0, then we are talking about irreversible process. And when the entropy generated is equal to 0, then we are talking about the reversible process. But when the entropy generation is less than 0, then we are talking about impossible process. I hope this makes sense. This is a summary of all what we've said so far. Does this make sense, please? Okay. This relation serves as a criterion in determining whether a process is reversible, irreversible, or impossible. Some remarks on entropy. So this remarks is just talking about what we have over here. So I think we can skip that. Then move on to the third session. We talk about isentropic process. And when it's talk of isentropic process, we are talking about a system or a change of system at a constant entropy. Okay, we said isothermal is a constant temperature. And we also say isochoric is a constant volume. We talk about adiabatic and all that. So isentropic is a thermodynamic property that happens at a constant entropy. But you and I also know that when you are talking about entropy, we also talk about heat. Okay, heat energy. So isentropic can also sometimes be related to adiabatic process. Okay. We have already stated in our previous studies that entropy of a phase mass can be changed by heat transfer and irreversible. Okay. And it follows that the entropy of a phase mass does not change during a process that is irreversible and adiabatic, as shown in figure 5. And now let's see figure 5. And this is figure 5. So if you are talking from the entropy of this one to this one of a mass, and there's no heat transfer, it means the mass that we have for the initial state will be the same as for the final state. That's mass in terms of entropy. For the initial state will be the same as what we have at the final state. Okay. A process during which a process during which the entropy remains constant is termed as entropic process. And such a process has the characteristic that the S is equal to 0, or change in the second state is the same as the change in the first state. So it means when you take any two states, the first state has the same properties as the final state or the second state, or the change in state is always equal to 0. Okay. This means that a substance will have the same entropy value at the end of the process as it does at the beginning, as long as the process is carried out in an isotropic manner. Okay. So in thermodynamics, it is a process involving change without any increase or decrease of entropy. Since the entropy always increases in a spontaneous process, you must consider reversible or quasi-static processes. During a reversible process, the quantity of the heat transferred is directly proportional to the system's entropy change. Systems which are thermally insulated from their surroundings undergo processes without any heat transfer, and such processes are called adiabatic. So if there is no heat transfer, as we stated already, or we've done already, that during an isotropic process, there are no dissipative effects, and the system neither absorbs or gives off heat. So when we are talking about this system as an adiabatic and isentropic process, it means this system does not dissipate heat. And when you say dissipate, it means it doesn't give off heat. Everything is constant. The heat in there is constant. Okay, so the heat that is used in the system is what is used for the entire change of states. And hence, the state entropy is also constant as you move from the first state S1 to S2. Okay. Many engineering systems or devices such as pumps, turbines, nozzles, and diffusers are essentially adiabatic in their operation. Yeah, so if you are talking about turbines and nozzles or all diffusers, they are adiabatic. Why? Because if you are trying to use a nozzle or diffuser and you are applying heat to it, at the end of the day, you might cause combustion. Because as it increases a little, it can ignite and combustion takes place. Meanwhile, we don't need any combustion. We just want to carry or change the state of the first process to the second process by maintaining constant heat. Okay. And they perform best when the irreversibility, such as the friction associated with the process are minimized. So when you minimize the friction, it makes the process possible, or it reduces the um, possibility of reversibilities happening. Okay. Therefore, an isotropic process can serve as an appropriate model for actual processes. Also, isentropic processes enable us to define efficiencies of processes to compare the actual performance of these devices to the performance under idealized conditions. It should be recognized that a reversible adiabatic processes is necessarily isentropic. That means change in state is always constant. But isentropic process is not necessarily a reversible adiabatic process. So when I'm talking about adiabatic process, it's not ideally a reversible process. Okay. The entropy increase of a substance during a process as a result of irreversibilities may be offset by a decrease in entropy as a result of heat losses, for example. So when I'm talking about isentropic process, because the change of state is always the same, sometimes there's some kind of loss of heat to keep the system constant. Okay. However, the term isentropic process is customarily used in thermodynamics to imply a reversible adiabatic process. Okay. Now they say, is it possible for the entropy of a closed system to be zero during a reversible process? And they say explain why. So yes, it's true. The explanation is also there. I'll leave that one too for you. Then go to the property diagrams of entropy. Now, if you are talking about property diagrams, then we can talk of the TDS and we can talk of the HDS as well. And the TDS talks about the temperature with respect to entropy, and the HDS also talk about it as respect to the entropy change. Okay. Perhaps property diagrams usually aid in the analysis of thermodynamic processes. There are two diagrams commonly used in the analysis of second law of thermodynamic or temperature entropy and enthalpy entropy diagrams. So when I'm talking about the diagrams that helps in analyzing the second law, they are always either temperature entropy change or enthalpy entropy change. Okay. And the first one that we saw for the unit one, session one, was temperature entropy change. The one we had, the reversible and the irreversible, is the temperature entropy change. And we also have the enthalpy entropy change. Okay. Now let's consider equation 1.3, that the equation we saw earlier on. So if we rearrange it, you have that of the heat change in the reversible reaction to be that of TDS, where the T is the temperature and the DS is the entropy. So if you try to draw a temperature against entropy, the change in the cycle is known as the heat or the reversible heat. Okay. Now, this is how to go by that. So you have heat, the temperature against entropy. And if you look at this expression here, temperature against entropy. So it means when you plot a graph of T against S, you are going to get a slope or a gradient to be what? The heat. So it means when you take this diagram, the area under this diagram is known as the heat. The area under this diagram is known as the heat. Or the gradient is known as the heat. I hope you are making sense. Because
Yes,
I know you guys do math, so this has nothing to do with physics, it's purely math. Okay. Now, if you take the portion that will be labeled the A, it means even under this whole thing, you are trying to take a small portion of the area, and that is the dA, and it's given by TDS, and it's equal to what? The change of heat between these 2 points. Okay. The entire area is known as the heat that is being transferred or heat within the system. That's from this internal reversible process. But if you take this small portion within that reversible process, we have a small change in heat. But if you have to take the whole thing, it's given by the total heat within the system. Please, I hope you are making sense.
Yes, please.
Okay, sure. So from figure 6, the QV, so the Q in the reversible reaction represents a differential area under the TS diagram. The total heat transferring during a reversible process is determined using the integration as this. And yes, it's true, because if you want to find a change from here to here, it's given by this. And when you do that, you are going to get the heat that is being transferred in the system. And that's what is being done here. And this represents the area under the process curve of the TS diagram, that's the temperature entropy diagram. Due to this, we can conclude that the area under the process curve on the temperature entropy diagram corresponds to the heat transfer during a reversible process. And we stated that already. The area has no meaning for irreversible processes. Means when I'm talking about the area, that's the heat here, it has no meaning for irreversible processes. Okay. We can also, we can also express equations 1.14 and 1.15 using unit masses as that's 1.16 and 1.17. Means you are trying to just use this same thing, and it's the same as what we have over here. And we've not changed anything. I hope you know that. Because if you integrate this, we are going to get rid of that of the differential value here, so that I have the Q reversible as the same as that, and it's the same. So it means if you represent a differential for a differential to this value, you have the Q is equal to, then the D will cancel the integral form, then have TDS, and that's what you have over here. We've not changed anything. Okay. We need to know the relationships between existing between T and S before integrations in equation 1.15 and 1.17 could be performed. So as we said, we need to know the difference between the small s and the big S. And we said that big S is for entropy in extensive property, entropy as an extensive property, and the small s is entropy as intensive property. Okay. If the process is a reversible isothermal process, if the process is a reversible isothermal one, then we have the equations yielding that has a K reversible to T naught change in temperature. And that of the 1.16, that's the entropy as K reversible to T naught change in S. Then you are seeing there are no change. It's the same thing that you are having here, just that the entropy here, this is represented as an extensive property, while this is treated as intensive property. Okay. So when we talk about this, we can talk about this in terms of temperature change or something. Because temperature change as an extensive property, it means we can see difference between one state to another with respect to temperature, but we can't see or we can't visualize the change. But as in intensive property, you could see the change. It means there could be increase in volume or something. And when volume of something increases, you could really see with your eyes, or you can observe with your eyes. Okay. In which T naught is the constant temperature and change in S the entropy change of the system during the process. On a TS diagram, that's temperature entropy diagram, the isentropic process appears as a vertical line segment as shown in figure 7. So if you take figure 7, yes. So figure 7, when you take an entropy change, because we said if we talk about isentropic, it takes place at a constant what? Entropy. So if you are changing from the first state to the second state, it means here there's change in temperature. The temperature has reduced, but the entropy is still the same. So from state 1 to state 2, there will be temperature difference, but the entropy still remains constant. Okay. On a T, the isentropic process appears as a vertical line segment shown in figure 7. This occurs because an isentropic process involves no heat transfer, so that the area under the process path must be 0. So if you look at this, the change in temperature, but the isentropic change is 0. And also we made mention that heat is different from temperature. Heat is different from temperature. Okay. We need the TS diagrams as valuable tools to visualize the second law of thermodynamics in respect of processes and cycles. Engineers also make use of the enthalpy entropy diagram. This diagram is valuable in the analysis of steady flow devices such as turbines, compressors, and nozzles. Enthalpy is a primary property in the first law analysis of the steady flow devices, and entropy is a property that accounts for irreversibility during adiabatic processes. As an example, in the steady flow of steam through an adiabatic turbine, the vertical distance between the inlet and the exit states that are shown in H is a measure of the work output in the turbine, and the horizontal distance, ds, is a measure of the irreversibilities associated with the process as shown in figure 8. So this is the figure 8. So when I'm talking about changing this to 2, you can have change in H, and that of changing 1 to 2, you can also have change in entropy change. So in this state, we have change in enthalpy and we also have change in entropy. I hope you are making sense. When you look at this graph, the change is with respect to only the temperature, that's the vertical aspect. But when you talk about the enthalpy entropy change, realize we have change in the enthalpy and we have also change in the entropy. Okay.
Okay.
The vertical distance, the H on the HS diagram for adiabatic steady flow devices is a measure of work, while the horizontal distance is the measure of irreversibilities, that's the entropy. And that brings us to the end of that one as well. Then we come to the section 5, that's the third law of thermodynamics and its consequences. And as usual, this will be the last one, then the unit section 6 will be for you guys. Okay. Now the third law, we have been talking about entropy since the beginning of this. We have been talking about, yeah, hello. Okay. We have been talking about entropy since the beginning of this unit and know that entropy is a useful property and serve as a valuable tool in the second law analysis of engineering devices. Does this mean that we know and understand entropy? So we are just talking about entropy as engineering properties and concerning second law. But do we really know and understand entropy? Okay, and the answer is no. So why are they saying no? This does not mean entropy is not useful. In our analysis of the first law of thermodynamics, we could not define energy, yet it did not interfere with our understanding of energy transformations and the conservation of energy principle. So yes, they're saying in the first session, we couldn't give a vivid definition for energy, but we were able to find when there is change in energy in a the thermodynamic state or system. Okay. That's the same as entropy. We are able to define or differentiate or establish its entropy change. We can also consider entropy as a measure of molecular disorder or the randomness associated with molecules. When systems become increasingly disordered, the molecular positions become less predictable and the entropy increases. This is the reason why the entropy of a substance is lowest in the solid state and highest in the gaseous state. So they are saying when you are talking about entropy, it's very high in the gaseous state and it's very low in the metallic state or solid state. Why? Because when you are talking about entropy, we talk about its measure in terms of molecular disorderness. And when you are talking about molecular disorderness, they have a random movement when you are talking about gaseous substances. Because when you take a solid, the molecules are in order. That's why it's very solid. That's why it's solid or it's very difficult to break. But when you talk about gas, the molecules are moving randomly. They move freely. So when you are talking about entropy, it's best or it's highest in the gaseous state as compared to that of the solid state. The entropy of a liquid is between those of a solid and gas. The molecules of a substance in solid phase oscillate continually about their equilibrium positions. They cannot move relative to each other. Yes, so when we talk about solid, they cannot move relative to each other, but for a gaseous, they can. Their positions at any instant can be predicted with very good certainty. So when we talk about a solid, to predict the molecules in a solid medium is very easy and is very certain. It's very certain. If you do that, you are sure that what you are doing is the right thing, or it's kind of more accurate as compared to that of gaseous one, because with gaseous, as we said, they move randomly. So maybe ideally, what you might think or the uncertainty of locating a molecule in a gaseous system is very difficult, because assuming to say, okay, let me put it in this way, like you are coming from Accra to Cape Coast, and the road is just one way. Okay, it's just one way, just the main road that you know. And let's say it's a 4 hours journey. So 4 hours journey, when you move from Accra, and from Accra to Cape Coast, as I said, it's 4 hours journey, and you move in the next 1 hour, we can do calculations and know that there is the point that we got into when we are using our kilometers and the speed. We know all that. We can locate your position in 1 hour time. But when we are coming from Cape Coast to, let's say, Kumasi, and I don't have any defined path, say ubetimi ayera, so ubetimi you see airplane, so ubetimi afaka, so ubetimi anante, and you don't know the path you are taking. Either say oh yeah before beira, either say you are coming with a private jet, ubetu, either say oh the car neighbor, or either you are walking. We don't know the one you are using. It's very difficult to predict where you are at any given time. Right, so the same thing applies to what we are trying to say. When you are talking about solid, because the molecules are packed and intact, to predict the molecule at any point in time is very certain. But when you are talking about it in terms of gaseous, it's not certain, because they move randomly and freely within the system. Okay. Their positions at any instant can be predicted very good certainty. In the gas state, we are here. In the gas state, however, the gas molecule moves about at random while colliding with each other. They change direction and make extremely difficult to predict with accuracy in the microscopic state of the system at any instant. So as we said, it's very difficult when you are trying to find the molecules at a specific point. This molecular chaos gives the gas phase a high value of entropy, and because of that, it gives it a very high entropy. In the microscopic view, an isolated system that appears to be at equilibrium state may exhibit a high level of activity due to the fact that the molecules are in continuous motion. There are a large number of possible microscopic states of molecular configurations corresponding to each state of macroscopic equilibrium. So we are talking about two things here. We are talking about the microscopic states, and also we are trying to relate its configurations to the macroscopic equilibrium. Okay. The entropy of a system which is in a particular macro state is related to the total number of possible microscopic states of that system, called the thermodynamic probability. That's omega by the Boltzmann relation. This relation is expressed as dust. So when you want to find the macroscopic property in terms of the entropy state, we say it's given by the Boltzmann constant and the lane of that of the omega, where the omega talks about the thermodynamic property. Okay. Where K is given by this and is constant. We are assuming that the system is in a particular macro state which has a fixed energy, and this situation is known as a macrocanonical ensemble. Therefore, from a macroscopic point of view, the entropy of a system increases whenever the molecular randomness or uncertainty of a system increases. We are just trying to state that when we talk about the entropy of a system, which their movement of the molecules are randomly, they are always increasing at any time. They are always increasing at any time. And this is valid for gaseous system, because as we said, solid, the molecules are not moved randomly or freely. We have already stated that the molecules of a substance in a solid state will vibrate continuously, thereby creating an uncertainty about their position. As the temperature is decreased, these oscillations, however, will fade and the molecules become motionless at absolute zero. So this statement is also true. You know, if you have a solid and we heat the solid, we are trying to create vibrations for the molecules. And if that happens, movement of the certainty for you to locate a molecule becomes quite difficult a little. But then when there's no heat applied to it, or there's no heat applied to it, or the metal is at an absolute zero, then the certainty of determining the particle or the molecule at any time or any instance becomes very easy. This signifies a state of ultimate molecular order and thus has minimum energy. We can state that the entropy of a pure crystalline substance at absolute zero temperature is zero. So if you talk about a pure crystalline substance at an absolute zero temperature, the entropy is always zero. Why? Because there's no uncertainty about the state of molecules at that instant. So as we said, the entropy of a system is always defined by the movement of the molecules. Okay. This statement of the third law of thermodynamics, that this statement is made of the third law of the thermodynamics. The entropy determined relative to this point is called absolute entropy, and it is useful in thermodynamic analysis of chemical reactions. Note that entropy of a substance is not pure crystalline, such as solid solution. It's not zero at absolute zero temperature. This is because more than one molecular configurations exist for such substances, which introduces some uncertainty about the microscopic state of the substance. Then go to everyday activity involving entropy and entropy generation. I think this is all reading. I don't know why we are doing this. Okay. The concept of entropy can also be applied to other areas. Thus, entropy can be viewed as a measure of disorder or disorganization of a system. So as we said, entropy has to do with molecule movement, either being random movement or defined movements. But when you're talking about entropy, it's most often used to define the randomness or the movement of these molecules in a system, or how they are being ordered or how they are being disordered. So ideally, if you want to find how a system there is disorganized in a system, or how the molecules are disorganized or moving in a system, then means we are looking for the entropy of the system. Okay. Likewise, entropy generation can be viewed as a measure of disorder or disorganization generated during the process. The concept of entropy is not used in daily life nearly as extensive as the concept of energy, even though entropy is readily applicable to various aspects of daily life, yes. So when we talk about entropy, it's not, though it's being applied in our everyday life, but it's not as that of the energy change. Why? Because if you are talking about entropy, you always know, for example, if you are coming from Accra to Cape Coast, ideally 4 hours, you have to be here. So if by 4 hours I call and you are not in Cape Coast, probably then it means you've passed somewhere. So because it's always, we have that kind of mentality and we have those kind of organized system, it's not really applied in everyday, but rather the energy that we use, that's maybe when we are coming, there were some activities we did or something that made you lose some energy or gain some energy. That one becomes the cause for us to analyze what that was. But for you to move from that place to this place is kind of a defined thing. So for entropy, even though it's applied in our everyday activity, but it's not that applied as much as talk about the energy. Next, we present several ordinary events and show their relevance to the concept of entropy and entropy generation. Efficient people lead low entropy. This statement dissuades me. Efficient people lead low entropy life. Efficient people lead low entropy lives. So if you are talking about efficient people, it means everything they do is highly organized. Please, are you making sense? Hey. Why are there no low entropy people here?
Yes, sir. Yes, sir, we are here.
Yes, that statement they sweet me, pan. They said efficient people lead low entropy life. It means they are highly organized. Okay. They have a place for everything. That means at any point, uncertainty of determining whatever they are doing or what they are doing is very low. So you can very know wherever okay. And it takes minimum energy for them to locate something because everything is organized. It takes very low time or very small energy for them to find whatever they are looking for. And now, inefficient people, on the other hand, are disorganized and lead high entropy lives. And it takes them minutes or hours to find something they need, and they are likely to create a bigger disorderness as they are searching, since they would probably conduct the search in a disorganized manner. Yes, so we all need to be I don't know if I should say this or I shouldn't. We all need to be a low entropy people so that our life will be very efficient and so easy to maneuver our way out for a success and a great work and a good life and healthy life as well. People leading high entropy lifestyles are always on the run and never seem to catch up. Yes, they are not sure there. So you need to put yourself in orderliness or a low entropy. You probably notice that some people seem to learn fast and remember well what they learn. We can call this type of learning organized or low entropy learning. These people make a consciousness effort to file the new information properly by relating it to their existing knowledge and creating a solid information network in their minds. So when you talk about low entropy people, they try to link things so that it becomes easy when they are trying to capture everything. Okay. So in as much as you've done so many phases courses, you should be able to relate how one course is related to each other so that you can make meaning from the basic ones that we did. And when you are trying to do that, we are talking about you having low entropy. But if you learn something and you forget and you come and learn new thing and it's now up to you for you to start the whole thing again, I just also could do baba. Now then it means you have a very high entropy. If you do that, you are in trouble. Always now as a quiz and exams are when you're prepared, those kind of things. But if you're able to relate everything in orderness, it means your entropy level is very low and it becomes so easy to maneuver your way out and also try to link things in order. Okay. On the other hand, people who throw the information into their minds as they study with no effort to secure it may think they are learning. They are bound to discover otherwise when they need to locate the information. For example, during a test, it is not easy to retrieve information from a database that is, in a sense, in the gas phase. Students who have backouts during tests should re-examine their study habits. So students who blackout, it means at the end I was he did not try to relate anything. No, so any small thing, no call blackout because he can't really locate where he was an question. So bet no adwendwen saa by the time at the end I was wako who ni 3 mile beba not just a time crash. And that's what we call blackouts. Obeju paper or like a quiz or exams, you just take your paper at that instant, then you go blank, you don't remember anything. Just some few minutes to the end of the paper, that's where whatever you learned, you start remembering them. And that's what we call blackouts. It means you have a very high entropy. You don't try to relate whatever you learned, still put them in disorderness. So it becomes difficult to locate some of the information you really need. Okay. A library with a good shelving and indexing system can be viewed as a low entropy library because of the high level of organization. So if you come to UCC library, everything is in order. When you want book for sciences, you have the floor. If you want book for literature, you have the floor that you can get, or the sections you can get, or those kind of things. So when you talk about those libraries, you see the entropy level is very low because it's easy to find the book or find the database or the journal you are looking for as compared to high entropy libraries. Likewise, a library with a poor shelving and indexing system can be viewed as high entropy library because of the high level of disorganization. A library with no indexing system is like no library, since a book is of no value if it cannot be found. So if you have a library and it has no indexing, they are saying that it is no library. And as for that, entropy is infinity. So it's highly difficult for you to locate a material or an item. Okay. Consider 2 identical buildings, each containing 1 million books. The first building, the books are piled on the top of each other Whereas in the second building, they are highly organized, shelved, and indexed for easy reference. There is no doubt about which building a student will prefer to go to for checking out a certain book. Yes, some may argue from the first law point of view that these two buildings are equivalent since the mass and knowledge content of of the two books are identical. And yes, it's true. If you take two buildings and let's say the number of books or the type of books is in the first building, the same as that of in the second building. Yes, some people will argue that because the books are the same, so it means the energy between these two systems or the quantity of items or knowledge in the same two buildings is the same. But when you are talking about it in terms of entropy, it's never true. Why? Because when you take the first one, where the items were well arranged, to locate a book, it can take you just some few minutes, hence it has low entropy. But when you go to the second room where the books have been scattered, it have been arranged on each other without a proper indexing or proper arrangement, you can take the whole day looking for that same book. Someone use 5 minutes to locate it, and you cannot still find it. So when you talk about that, even though the quantity of book or the quantity of knowledge in the buildings are the same, the probability of locating a specific material becomes very difficult in the second one as compared to the one that have a very organized and shared materials. Okay. There is no doubt about which building a student will prefer to go to for checking out a certain book. Yes, some may argue from the first law point of view that these two buildings are equivalent since the mass and knowledge content of the two buildings are identical, despite the high level of disorganization, that's entropy in the first building. This example illustrates that any realistic comparison should involve the second law point of view. So if you are trying to, yes, some people argument it's always true, but then the fact that your argument is true doesn't mean you have to say, you have to talk, excuse me for my word, foolishly. And that's what some people always do. They try to compare two things with the same quantity, not talking about in terms of easy to access. Okay. And those things need to be stopped. Example, the other day, I think we are talking about politics in the sense that one can, if Mr. Michael becomes the president of Ghana, maybe he can do the thing well, and you guys will agree, right? The same thing applies here. We have two systems or two governments here, assuming even though when they all come, like at the end of the day, but if one comes and you see that, oh, the level of organized and the disorganized is being high as compared to the other, you can't really compare the two to be the same, because if one comes and is able to make maneuver your way out with things is quite better, then that can ideally be taken as the good one. Not the fact that because they are all going to spend the same years or they are always going to have the same final output means they are always the same. So when you are arguing, don't always argue about the fact that at the end of the day they all have the same thing, but argue about the fact that the organized, how organized one is has to be also in terms of the argument. So don't always talk about the quantity or the amount only, but also talk about the organized or the disorganized aspect as well, or the otherness. And that will make the whole thing sound. Because as at now, we are all now scientists, so you shouldn't be talking just like the home accounts or the business or the general ask people. You have to talk for the scientific point of view so that at least it will really be sound for everyone to understand you and for people to appreciate you. Okay. There's no doubt about which we all we've read here. Yes, some many argue about the first law of the two building. The example illustrates that many realistic comparisons should involve the second law point of view. Two textbooks that seem to be identical because both cover basically the same topics and present the same information may actually be very different depending on how they cover the topics. Yes, so if we take two topics, two books, let's say I don't know the content. I'm just making an example. So please don't really take my words in the wrong way. Let's say we are taking approaches series and let's say Akiola. Okay. And let's say we are taking the physics textbook for those two publications. Now, if we take the two publications, they must all treat the same topic. But at the end of the day, who have a better arrangements? Who made it easy to understand? Okay, and when we talk about that, we also talk about it in terms of entropy. So that the one that seems to be easy to understand have a very low entropy as compared to the one that have more information but it's not well organized. So if you take some and it's even applied to some of you your exams. I think last year I marked some people's paper and you realize the paper is about 12 pages. Over to me, they just 4 pages, and the person will do a very neat work with everything on point. What shall I say, 50/60. We read 12 pages, not the extra sheet. And so the things are not in well order. So it doesn't make sense. And at the end of the day, you realize the person has high entropy, and the man will endorse be brave, and also church and you don't really put them in orderness. And you really need to take note of this. So as I said, I don't always want the chew and pour. It's about how you understand it and relate it so that if you put it in your own words and it makes sense, you get your marks and you go. Don't go and write and could do baba because if a very low entropy person is marking your paper, he marks it or read it according to orderness. Okay. It may be first step, it relates to the second step, relate to the third step. And even if the steps are 10, but you skip 5, but the 5 that you wrote, it was in orderness, the person will give you your marks and you go. But upper 10 never become one other 10 about just miss them. Maybe no more marks. But more I have because you can't really relate the ideas. You are just writing for writing's sake. But at the end of the day, you are trying to lay, like you are arguing. So your prepositions must follow. Okay, so that's when you conclude, you must follow that, oh, okay, based on the prepositions that you've listed, all the claims supports or the conclusion, all the claims support the conclusion, then you get your marks. But so when you be nice, I don't know, I just want you wasting your time and also worrying my mind. Because when I'm able mark, I have to read everything. And with me, okay. After all, two seemingly identical cars are not so identical if one goes 1/2 as many miles as the other one on the same amount of work. Likewise, two seemingly identical books are not so identical if it takes twice so long to learn a topic from one of them as it does from the other. Thus, comparisons made on the basis of first law may only be highly misleading. Yeah, so if you are talking about the first law as far as, you are making comparisons as far as the first law is concerned. You are talking about in terms of quantity or topics. Yes, it might be true or it might mislead you. But if you are talking about it in terms of orderliness or organized, then means you are talking about it in terms of the second law and the entropy law, and that will make it, or the second law, and that will make it very interesting and very sensible. Okay. Having a disorganized, that's high entropy army is like having no army at all. Yes. It is no coincidence that the command centers of many armed forces are among the primary targets during the war. One army that consists of 10 divisions is 10 times more powerful than 10 armies each consisting of a single division. Likewise, one country that consists of 10 states is more powerful than 10 countries, each consisting of a single state. The United States would not be such powerful country if there were 50 independent countries in this place instead of a single country with 50 states. The European Union has the potential to be a new economic and political superpower. The old glitch, divide and conquer, can be rephrased as increased and entropy and conquer. Okay. So that brings us to the end of session 5 as well. So the session 5 was trying to talk about entropy as far as our daily life is concerned. So we talk about entropy in terms of a solid material, which is well organized, or it has a very low entropy. That we say if you take, let's say, Accra to Kumasi, Accra to Cape Coast, at any point in time, since we know the hours to this place, we can define the, or based on the hours, we can know the particular point you got into if you are come to this place. When we talk about gaseous states, that's where it becomes very difficult to locate one's position at any given time. And also talk about entropy in our daily life, where we say, as a human being, at least you have to be happy, low entropy, so that life will be so smooth and efficient for each and every one. Okay. Then we go to Unit 6, we talk about the Joule expansion, and that is meant for you. And ideally, it's not anything. It's trying to talk about expansion of a system. So if you look at, I'm trying to give you the general overview so that when you go, you sit down, you really and get it. So when you look at this system, right, it's the same identical system, but rather it has been clipped. And the volume and pressure in this volume is now allowed to be filled the whole container. So at the end of the day, you are going to have the same volume and the same pressure in the whole container, because this container was empty and the pressure and the volume of this one have been distributed for some to come to this one. And that's what you are seeing here. So there's no change in everything. And they try to relate the gas law that PV is called to NRT to it, and now find the pressure and volume at each point in time. So this is not any big deal. And that is all for you to do it. And that brings us to the end of today's class. Please, any question? Please, any question?
Hello, sir.
Yes.
Sir, it means that we will not meet again, right? The
No,
next
we
time will
meet
be our
tomorrow
quiz,
for
or we'll
the.
meet.
You meet tomorrow for the Unit 6.
Okay. I hope that tomorrow, at least, you will be told the areas to learn for the quiz. First quiz.
Oh, that one, Dr. Peter has to do that because I have no
Yeah,
idea
he
what
told us. He told us that it can be done. Well, like the last time you joined us, we pleaded that at
Yes,
least
he
for
said
the
that.
quiz.
Yeah, I know he said that, but then I've not contacted.
Please consult him.
So kindly do that for us. We beg. Kindly
Yes,
do that
because
for
I
us.
don't know.
Sometimes you go in for the quiz and then you see that all the questions are coming from Unit 6. Meanwhile, so we beg just for the first quiz. He said it can be done, so we beg, do it on our behalf. We beg.
Mr. George,
Thank you.
I will do that. I will do that, but you have to have a low entropy too.
we know. We have low entropy, but all of us we have low entropy. Thank you.
I'll do that. And I don't know. The other day he was saying, he told me the other sectors, they've not been able to get to the part we got into. So I was thinking maybe you said you would tell me to stop the 5 and 6 so that we just saw some questions, but then he didn't get to me. That's why we are doing the 5. But maybe after the class, I'll just contact him, and whatever that comes up, I'll draw your attention.
Thank you very much.
Still,
thank you.
Better still, right? You guys, the group, he's on the platform. Why don't you question him from that platform?
Sir, please do it on our behalf.
So it is too broad, though. Like sometimes you
The
see,
thing is,
sometimes it
see,
depends on the number of people. There are a lot of people. So sometimes when you are the person you are even talking to might not even see who that you were he was the one you were the question was asked, and there are a lot of people on the page. So if it can be one-on-one, it will be okay. And most of us don't also know that maybe this is the person. That's why we said do it on our behalf. As for the
okay,
page,
then
it is
let's do
too
it this
broad. We
way.
have biology people there,
Let's
we
do it
have
this
chemistry
way.
people there. So
Let's do it this way. Create a WhatsApp group, right? And name it thermal physics, and add me to the group, and make me an admin, so that I'll go and add him as well. Then you ask that question on the platform. Then I can talk on your behalf, because if I go to him on your behalf, it will be like, why am I the one fighting for you guys? Can't you guys say it? I don't know if you understand from that concept.
It's true, well understood.
it's a
Yes.
nice idea. It's a nice idea.
So create that
So
group,
I hope
add
maybe
me, make
Castro
me
will
an
do it.
admin.
If
I'll add you.
Castro can do it, if you can't do it, you can let me know, Castro, so that I will start. That will be a nice idea.
Yeah, so you can do that, so
We
that I'll add you.
personally
Go out to
to
agreement.
say, should we name it thermal physics, or because we have physics group too?
Said thermal.
That
No.
everybody doing physics.
Just this course, just the thermal physics only.
Okay.
So those doing the thermal physics only should be added, not any other
My
one. So that it should be a conversation between the thermal physics. So if there's any information maybe I want to give you with regard to the thermal physics, I can put it on that platform. That's why I don't want to talk on the other platform, because it's comprised of a whole lot. And all the lecturers are also on that platform, all the course coordinators. But this one is for thermal physics only, so that
Okay,
when they are
but
addressing the issue
sir,
regards to that, it will be easy.
Cody, what about also maybe using the physics platform that we have? Because since everybody on that platform is also doing the same course, so that it could just be straight ahead instead of probably generating an entirely new one. I don't
That
know.
will also bring an intruder, because when you talk about that physics course group,
Yes,
we have
you are
other
right
physics
to
courses
that.
like the atomic and modern physics and all those kind of things. So the
Yeah.
coordinators are also there.
Oh, okay.
Yes.
All right.
So this is supposed to be thermal physics purely.
Okay, all right.
Yeah. So if you're able to do that, I can assist you on that probably today. Because I don't know. I should have called him before the class have started to know whether I should do this or we should revise again, because he was saying that other sectors have not done up to this point. So you do that. Let's finalize that so that we know whether tomorrow you meet with part to the unit 6, or you just go back to some of the things that you didn't understand, and maybe you do that. Okay. So in the absence of this, then I guess you can call it a day.
All right, sir. Nice.
Okay, sir. So I'll do that. Maybe I'll talk to Castro. If he can't do it, then I'll do it. But I think
Okay.
Castro is not even on this.
I don't think
know
he's
whether
part
he's
of
here
this
because
course.
Why don't you do it? Do
he's
it.
not part.
Yeah, so
Okay, I'll do it. Don't
just the
worry, I'll do
people
it.
that do thermal
So
physics supposed to be on that platform.
Okay. I'll do it and put it on the main page and put a link there so that people can join.
Yes.
Okay. So thank you.
All right.
Hello, George. Hello, Bismarck. Bismarck.
Hello. Hello, I can hear. Hello.
Hello.